Hello everyone, I'm Rob Taylor. I'm the CTO at a company called Chipflow, and let's see if this works. And the talk I'm going to give to you today is on fast FPGA and IC prototyping with Python for automotive and industrial. And I also like to call this one chip on my shoulder. So I've been doing embedded systems now. I mean, I was an early mover in using open source and embedded systems back in 2000. Here's a lovely picture of me about then. In my first, I guess it was a Motorola, a PowerPC board running with Linux. Forgot her. And my early days very much spent working in the mobile space. I was working Nokia on what they were then calling web tablets. This was about 2000, a couple of years before the iPhone came out. Then helped build a lot of the automotive companies moved towards Linux in their in-car entertainment systems, which cross entertainment technology as well. And we worked with Arm a bit on some of the prototyping, and one consistent issue I found all through this. Yeah, excellent. I think that's good. I like to see people say things. Thank you. Always the chips, always the point, right? Especially when you're on the cutting edge of things. You got silicon errata, you're building drivers, things which are behaving the way that they're supposed to. The hardware choices you make at the start of the project tend to end up being wrong at the end of the project. And so, a couple of years ago, I was thinking, is there a way to actually do something about this? If you're looking at it, if you've got a suitably large volume of market, got a couple of options. You can build your own chips. And one of the best experiences I've had actually was working with Nokia, because we had a really close working relationship with TI, the Mark II, Mark III. We really there was direct feedback. We had engineers on site. I've never had that since, right? That model died probably about 2007, I guess. Other than they don't use the FPGAs, which I'm sure everyone here knows a lot about, which is less investment, but you are going to want to be bought, right? Depending on what you do, right? Doing it really simply, you get a nice cheap Chinese FPGA in the and of course you also got the your supply chain questions as well. I'm sure everyone hit fun supply chain issues in the last 4 years or so. And so that's an interesting thing to get around that. So, background in open source, comes to the rescue. And I started digging in on this many years ago now, I guess. And there's been a really interesting long history of open source tools, chip design. It's the big guys don't like to admit that it's there or what it's capable of. But there's been a long history, and some really interesting stuff. The Open Titan guys, they've just done the first commercial, fully open source chip design for security, the security module. Got a lot of groups, and even software going all the way back to the 90s, right? And some newer stuff funded by both EU, US governments. And some sort of interesting Chinese stuff as well. And then there was a really big push at some point on from Google on this, and providing free tape outs for objects. It's an interesting thing that may still continue. And so what we built here was, can we build a modern development environment, something that is comfortable for software guys as much as for hardware guys and girls? That allows you to both target an FPGA and actually build an IC in the end, right? So you've got that, because one of the biggest problems with when you're going to build a chip, it's a big decision for management, right? You know, it's, okay, right, we're going to put down 10 mil for the first year. We're hiring the team, paying tools. I mean, the cost per engineer is going to be somewhere around 500k a year, 400k a year, because you're going to pay the license for the software. They can cut all that out. And so we've got kind of like, you know, GitHub-based environments where you can write code, target your FPGA, run it in simulation locally, but then also in the back end, you've got constant tape-out happening that's, you know, working with our foundry partners and our OSAT partners. So you actually are always ready to actually tape out a chip, right? Whenever you're confident in. So that's what I'm going to talk about a little bit today. One of the key things you probably need in all this is some really good debugging with timing information. So there's a nice VS Code environment here, gives you the full information. Actually, can even go like it's got an understanding of the design as well, so you've got that really kind of you can see these transactions and you see stuff at the level that's actually happening and directly related to the code base you're working with, right? So whether that's the current version of this has Verilog and Python support for doing hardware design, and we will be bringing out System Verilog, VHDL, and maybe some of the interesting pipeline C environments that are coming out, the open source. Then on the back end, you just plug this into your CI, right? Or you can run it from command line or your VS Code environment, get a build and get your feedback there. And it will also start, and in a later release, we'll actually have all the timing information come back from that, so you can check that you are actually within all your timing constraints. That's a bit hard to see, isn't it? Maybe we should switch the light out. I'm old school 633. Does that go? See that okay?
Yeah.
Excellent, excellent. So the whole idea of the Python side is really just to make the assemblage easier. I mean, you can actually use the Python to write anything that any digital design of any complexity, right? But where we find it really works really nicely is, you know, I've got some components and I'm plugging them together and I want to get something up and running quickly. And so the environment here, this is actually straight from the example code base. I'll give you a link at the end. As you can see, as well as building the IC, it's also generating the software, the IC that we're making, or the target FPGA environment. So we can set up our software generator or plugging in a CPU. This is actually an interesting CPU written entirely by Minerva. It's not, you know, it's a pretty simple, two-stage sort of, but there's a whole world of great open source ICs out there now. Open source RISC-V, of course. Stick in our arbiter. We're going to plug in our SPI flash. We're going to have some SRAM in there. And that will also the chip that'll actually generate from SRAM. We'll use the appropriate block RAM, your FPGA. Well, that's some GPIOs or some UART. And the nice I/O bus as well. We're plugging those into, and then we're going to generate the software and generate the design. So that'll give us our tape out with our timing information. I'll have a look at how it's done on timeout, on the area usage, block design. Well, it'll eventually have power domain design as well. Let's do one do I press a button?
You press the blank button at the bottom.
Near the play. It's a video, so yeah, I'm not really sure if how to make this play. Oh, play! There's a play button.
There you go.
No, that did the wrong thing. We can. PowerPoint. So you just go click play there.
Yeah, I'll do that. Yeah. Okay. There you go.
So what we're going to show here is actually kind of building the design for there's a built-in simulator here. So this is going to actually show you building your simulated design, running your software on it. So it's just show you what's going on. This is the design we just went over. And here's the a little simple kind of main.c for it. Just go through a few things, say hello in cat language. So you just go run, sim run, build. That was it, building a simulation and running it. And you see there's our main executing there. Exactly the same environment. You've got the same sort of thing that happens for going through an FPGA board. I was going to try and do that live today, but couldn't find my board in time. It's exactly the same on your FPGA board. And as well as that, you can actually have your kind of system level check, your system level verification in there. So the way that this happens in this framework is actually we know what behaviors we want the chip to exhibit as we're running the test set over it. So if we run sim check, what that does is actually measures all the checkpoints and checks that they're covering in the right areas and the right time in the right order. And that's kind of a nice little JSON file that describes that. I think that's the end of that video. Let's see if we can move on. Maybe? I think there was a few slides missing, but never mind.